Okay, with lesson 7.3, we're going to solve trigonometric equations. We have to be very careful about following the domain. And we're also going to have to really be familiar with the unit circle. Forgive me for using this note sheet. It uploaded from a PDF and it's a little bit faint. I've recopied the equations by hand off to the side. Let's solve cosine of theta equals 1/2. What you're going to see is time and again, what we'd like to know is which quadrants we're interested in. Cosine is positive, and we have this mnemonic. All students take calculus. It tells us that all trig functions are positive in the first quadrant. Sine is the only trig function positive in the second quadrant. Of course, it's a reciprocal function. Cosecant is also. Tangent and cotangent are positive in the third quadrant. Cosine and secant are positive in the fourth. So because I have a positive value of 1/2, I know I need to be in the first and fourth quadrant. Cosine, when you have a reference angle of pi over 3, you're actually going to have cosine equal 1/2. So in the first quadrant, we can say that we're at pi over 3. In the fourth quadrant, we're going to say 5 pi over 3. Technically, you could also say negative pi over 3. I'm going to say plus 2 pi k. There are no domain restrictions that say you can only go between 0 and pi. For both of these, k would have to be an integer. So we could go around the unit circle as many times as we'd like, either clockwise or counterclockwise. And then, of course, we would have, at these angles, cosine would equal 1/2. Let's do this next problem. Very similar. I'd like to isolate sine, and so I'll subtract a radical 3, and I'll divide by 2. There's a big difference here, though. You're going to see that really we're only involved with angles between 0 and 2 pi. Sine is negative, so I can't deal with the first quadrant or the second quadrant. Sine would be positive there. I'm only interested in the third and the fourth quadrants. The reference angle that we're going to be looking for, of course, would be pi over 3. Sine of pi over 3 would always yield a root 3 over 2. So what I can do, knowing that I am only between 0 and 2 pi, I could just say in this third quadrant here, we're of course going to have 4 pi over 3. And in the fourth quadrant, we'll have 5 pi over 3. Here I cannot say negative pi over 3. My angle must be positive in between 0 and 2 pi. Here I also cannot say that I can have plus 2 pi k. Sometimes kids want to do that, but saying plus 2 pi k will allow you to let k equal 1, k equal 2, k equal 3. And even though these angles would have sine being negative radical 3 over 2, these angles would be much larger than 4 pi over 3. In a similar way, if we let k equal negative 1 or negative 2, our angles would be negative and they'd work. They'd make sine of that angle be negative root 3 over 2, but we wouldn't be in the restricted angle measurements. For this next one, very, very big difference. You can see I've highlighted the 2 theta. I strongly, strongly recommend whenever the argument, the inside of a trig function, changes, that we just modify that by making a little substitution. I usually put in a w, and we'll solve for w. Now, sine is going to have a positive value, and I think it's pretty obvious, pretty evident, I hope, that we will have 2 quadrants that we are really looking for. A, all students in the first quadrant. S, the sine, is in the second. We'll need a reference angle, of course, of pi over 6. And in the first quadrant, we'll have pi over 6. Now I'm going to do something that might seem a little strange at first. I am going to put plus 2 pi k. And then we are going to have in the second quadrant, that would be 5 pi over 6. And again, I'll put plus 2 pi k. Now at first glance, this might seem counterintuitive. You might think, now wait just a minute, you said up above in the previous problem, we don't put plus 2 pi k because our angle boundaries are very much restricted between 0 and 2 pi. However, we have changed the period of this function. And whenever you're changing that with the argument, it is best to just write in a general sense what your plus 2 pi k is and then solve from there. I hope that will become clear in just a moment. If we were to solve substituting back in that 2 theta is equal to pi over 6 plus 2 pi k, when I would take half of every term here, or divide it by 2, I'd get pi over 12 plus pi k. In a very similar way, if we were to solve for theta after I plug in the 2 theta here, I'd take half of each term, divide it by 2 in other words. I'd have 5 pi over 12 plus pi k. Now if I didn't have any domain restrictions, these two equations here would be great. They would in fact represent everything that we would ever have for a possible solution. But when we're writing this plus pi k or 2 pi k or whatever it may be, we're representing an infinite number of angles. And we can generate particular angles by plugging in an integer. For example, if I plug in k equals 0, real quickly we'll see that we get pi over 12. If I were to let k equal 1, pi over 12 plus 1 pi would be the equivalent of pi over 12 plus 12 twelfths pi. This would yield 13 pi over 12. Next, you might wonder about plugging in k equals 2, but if I plug in k equals 2, I will be larger than 2 pi for my overall angle, and I'm not going to be able to have that. Similarly, if I let k equal negative 1, I will be having a negative theta value. Over here for this other equation, if I let k equal 0, I'd get theta is equal to 5 pi over 12. And if I let k equal 1, 5 pi over 12 plus pi would be 5 twelfths plus 12 twelfths, which is 17 twelfths. And of course we have a pi. There are in fact 4 answers. Any other k values would generate angles that are too large, bigger than 2 pi, or angles that are negative, that are smaller than 0. So whenever your argument changes, I strongly suggest that you substitute in a w and then very quickly make an adjustment. Let's move to this next one. Tangent of theta minus pi over 2 equals 1. Well, in a very similar way, we could say let's just look at the tangent of w equals 1. And again, we're only going to be between 0 and 2 pi. Tangent is positive, so let's see, we have all students take calculus. We'll be in quadrant 1 and in quadrant 3. And I guess what I want to point out to you, I hope it's clear, that our reference angle would be pi over 4. And in the third quadrant, we'd have 5 pi over 4. Now, whenever you have two angles connected by a straight line or a straight angle, we know from geometry that the measure of a straight angle is 180 degrees. We could also say that that's pi radians. So rather than write two equations here, we could just write pi over 4 plus pi k. And that's honestly what we should be doing. When I substitute back in that I have theta minus pi over 2, we can pretty much then solve for theta If I add pi over 2 on the left side, add pi over 2 on the right, I would get 3 pi over 4. Pi over 4 plus pi over 2 is 3 pi over 4 plus pi k. And in general, this would be a great solution, but I can only have answers between 0 and 2 pi, excuse me. So if we let k equal 0, theta would equal 3 pi over 4. If I let k equal 1, I'd have pi plus 3 pi over 4, so that's 4 fourths plus 3 fourths. That would be 7 pi over 4. If I let k equal 2, I'm too large. 2 pi plus 3 pi over 2 would just be too big. K equals negative 1 would be too small. It would yield a negative angle measure. So we will just have 3 pi over 4 and 7 pi over 4 for our final answer. Okay, using a calculator, the tangent of theta is equal to negative 2. I'd like to show you how to solve this graphically. And this might be a very nice way to solve this problem. Make sure your mode is on radians. And my left side, I'm going to type in the tangent of x. That's my y1. My y2, I'm going to type in negative 2. You can certainly go to zoom trig to get a quick picture as to what's occurring. However, our theta values, or our x values in this case, only go between 0 and 2 pi. So, making that adjustment, you can see here's my tangent graph, and my y2 was going to equal negative 2. You can see on this graph there are 2 intersection points. All we have to do is find those intersection points, and we can do that pretty quickly. We'll say first curve, of course that's my tangent. Second curve is the line y equals negative 2. Yes, we can put our cursor right over here. To the 100th, 2 decimal places, we'd get 2.03. But you might guess there is a second answer, and there is. There's a second intersection point. And first curve, you can say enter. Second curve, well, yeah, it is going to be this y2, y equals negative 2. The guess, you just have to get your cursor. I've hit enter for each of those. Put your cursor pretty close to where your intersection point is. You'd get about 5.18. So here are your 2 radian measurements. And we would only get 2 values. Now I want to point out you could also go back to earlier problems, all the ones we've done earlier in fact, and work them out from there. Doing it the same way graphically, you'd get the same answers. Moving on to the next problem, what if instead of having sine, what if I let w fill in for it? And if we did, we could see that this would factor. And in factor, it would factor into 2w minus 1 and w minus 1. And that would mean 2w minus 1 could equal 0, and w minus 1 could equal 0. We'd get w equals a half, and w would equal 1. This actually means sine of theta is a half, or sine of theta would equal 1. Now, we don't have any change to the period. I'm interested in where sine is positive 1/2, only in the first and second quadrant. That would be pi over 6. In the second quadrant, that would be 5 pi over 6. Where is sine equal to positive 1? Well, around the unit circle, just one place, pi over 2. We don't have to put any plus 2 pi k's. We're only between 0 and 2 pi. Okay, so we're going to leave off of here. There are a couple other problems that we're going to talk about, but hopefully this is going well.